but could do that without having their own fab, and that was the origin of fabless. Today, the fabless industry has well over 20% of the worldwide semiconductor revenue is all fabless. In fact, I would say this is probably more like 30, maybe 40%. I don't know the latest number, but market demand, so that's the good news, right? Now, what's the difference between fabless and IDM? So this chart here, again, this is now getting more information from my book, so if you want to delve into it, there's some nice chapters there that you can look at. So pictorially, if you look at the whole integrated circuit system chain, you'll start from system design, which would include hardware, software verification, chip level design, which has the chip architecture, specification, and verification, chip design that might have logic design, circuit design, intellectual property is a term that's used for blocks that can be reused. So, you know, if you think about the billions of transistor designs that are done, if there's some standard function, like certainly the inverter and the multiplexer and things like that, those can be put on in a library, and they can be reused for the second and the third chip, right? You don't have to design all the way down to the transistor level. An analog function, for instance, could be a voltage reference block. That could be designed once and used for multiple chips in the same technology. So those are IP blocks that are kind of reused, and that's become sort of an industry standard. There's design tools and physical design and tape out, so I think the Synopsys gentleman will talk about more detail on all of this stuff. And then from a technology development perspective, you got to have a process, a package, and an assembly technology. You got to actually do the implementation. Where you finish the design, the usual transition is to ship what's called a tape out. Refers to GDS2 tape sometimes. Is I don't know what GDS stands for, but there's a design database that connects all the transistors and the interconnect together to meet the functionality. And then you ship that to a TSMC type of, or SMIC fab that'll make the masks, make the wafer fab, make the silicon. You can get it tested, do a package and assembly, and ship the product, right? So this is the entire cycle. The big black box says that the IDM company does all of that. Samsung still does all of this today. Intel does all of it, almost all of it, right? And so that's where the IDM started off. The blue represents what the fabless companies might outsource, and then they would keep ownership of the top part themselves. And that's a sort of a win-win, right? Because Qualcomm is the #1 fabless company in the world. They don't have any of this, right? They have people that do library design. In fact, they would do the physical design on some of the chips themselves. So where that cutoff point is could be dependent on different companies and how exactly they do it. And that's sort of the detail in my book too, if you want to look at it. Here's an example of the BOM, bill of materials for a, let's see, this is an iPhone 5S. So a 16 gig, the way to read this is 16 gigabyte version. They back into a particular cost of manufacturing. So if it sells for $649, the margin is, this is what the cost is. And what's made up of the cost is these components. So in the red, I've identified some of the integrated circuits. Some of the disappointing things, of course, is here's a display. It's $41. So it's about $200 of cost of the parts. 20% of that is the display. Very little semiconductor stuff in there, right? And there's a display in there and some integrated circuits. But look at the processor. The wireless section, where's the processor? Here's the processor, $19. A lot cheaper than the display. The 2 billion transistor, you could argue the integrated circuit, the development cost is huge compared to what a display costs, right? But that's the way the market fills out, and I just show it here just so you have an idea of what the costs are in a BOM there, right? So this is data from a few years ago, but what was interesting is to look at the phones that for an iPhone 4, 24% of the components were made by fabless companies. For an iPad, a little over a half, and the HTC was 44%. So I think the numbers are probably even higher now. A little bit old information, but the idea that fabless is becoming a mainstream accepted methodology is extremely important. So what's involved in this? This top part is the same as what was on my Moore's Law chart. In the 90s, fabless companies become more formalized. And this is where the IDMs continue to do the entire fab assembly test themselves. And the way the evolution of this history is that people actually started outsourcing assembly and packaging much earlier, right, in the 70s. So companies that were based in the United States, even IDMs, they would go to Brazil, they would go to Korea, they go to, I don't think they went to China at that time, but to do the packaging, assembly and packaging. And then in the 87 timeframe when TSMC was formed, they started to outsource silicon into the foundries. And then in the late 90s, as companies like TSMC, UMC, and then later SMIC started to build the infrastructure even for design to provide the library, then they started to outsource the design. And a lot of design companies came about that would actually take the netlist or take the RTL and deliver a GDS2 tape. So that whole industry has evolved, and the purpose of this chart is to show you that of where we are, right? So you could ask the question, why do people want to go fabless? I show here capital investment. There's no scale on here, but basically to do an IDM, very expensive, right? We said $10 billion for a wafer fab. You have to build the design infrastructure and all that, so it's very expensive to be here. A fabless company, on the other hand, zero investment, right? All you can do is outsource the activity and get it done. So that's how they started, right? Companies like Qualcomm, no capital investment. They didn't know what it meant to invest even $100 million into something. What they have done, they have realized that if they did just this, they wouldn't be competitive with the leading edge IDMs. In fact, there was a, I started consulting for Qualcomm in 2006, and in fact, if I go back to this chart here, IDMs like TI, they had these wafer fabs, and they started to go fab light. TI would go to Wall Street analysts and tell them, hey, don't worry about Qualcomm. We've got the fab. We control the silicon. Qualcomm will never catch up. Guess what? In October of 2006, Qualcomm had a phone call with a 45 nanometer chip before TI ever had that chip. And the way they were able to do that is the way they interacted with the foundries. And they did this by selectively inserting a little bit of investment, more on the R&D side. So I actually helped them go to IMEC to learn advanced technology and build in products ahead of time. So that's, they used to call that IFM, is Integrated Fabless Manufacturing, and it required a little bit of investment. In the meantime, the fab light IDM companies were getting rid of some of their investments and going outside the wafer foundries. And then over time, I think these will probably converge, but the culture is very different. Coming from a culture where you're not used to spending any money, even spending $10 is expensive, right? So that's just more philosophical. There's some older data, but fundamentally the point I wanted to make here is that the share of the fabless industry keeps going up, and if you can figure out the reason, the growth rate of fabless companies is much higher than the rest of the semiconductor industry. So that's the business reason why this has happened. The other reason is that if you look at the return on equity, return on assets, these are financial terms, I'm not sure you're familiar with them, but these are all much better for fabless than they are for semiconductor company. And that's the reason why these companies have been successful. Now, the downside of fabless is to interact with the supply chain and make sure you get your parts when you need them. Because the fundamental difference between an IDM and a fabless company is that the CEO of Intel owns all of their packaging, all of their design, all of their fabs. If there's any conflict, any issues, that CEO can resolve it. The CEO of Qualcomm does not own the wafer fab, does not own the assembly and test. If there's any issue of delivery, guess what? He has to go talk to his counterpart or the people underneath, right? Point I'm making is your supply chain is outside your control. And managing that is a big challenge. So in the 90s, that used to be a big issue. Early 2000s, that's where my company came in. We used to do that service for startup companies. Since then, the supply chain has gotten a lot better. It's much more integrated. The ecosystem is set up, and it's much smoother than it used to be. And we've kind of migrated ourselves into a different area of expertise. But that's what my book teaches you, is how to do this and get that infrastructure set up. Fundamentally, it takes partnerships, it builds relationships. You got to make sure you're talking to the right people and they're communicating with them. It's not contracts. I mean, their contracts are there, but the relationships really matter, and people standing on their head to deliver your parts. Okay. You guys okay? No break required? Keep going? Okay. So I showed you a version of this chart earlier where it's more than more, right? Three-dimensional, 3D, more than more. And here, this is more and more on this side. And here, the opportunities are to do advanced lithography, advanced new materials, all that related to the more and more. But, and then adding new device structures, new processes for things like power devices. You know, you can do gallium nitride substrates and silicon carbide substrates and combine that with analog design for higher voltage, higher power devices. You can also do interconnect and heterogeneous integration. So I'll talk about that next. Right? 2.5D, 2D is where you're doing normal packaging. 2.5D is some integration, and then 3D is some novel structures that you can build. So here's a chart from 7 years ago. Greg DeLoggy again was showing the example of how you can do package integration. So traditional in the early 90s, what you would do is you had a printed circuit board, you had a processor, you had a dynamic memory, and a flash memory. Remember we talked about earlier, when this memory has to talk to the processor, signal goes something like that, right? All the way in the printed circuit board and all the way up there. Then what people started to do is, in the early 2000s, they would stack multiple memory chips on top of a logic chip and wire bond them. So these are wire connections, very fascinating to look at some of these cross sections. And so now the signal goes from the logic through the wire into the memory. Much shorter, much lower RC delays, and therefore the performance got better. By the way, if you opened up parts in around the 2005 timeframe, Qualcomm parts that looked like a single chip, they might have 2 or 3 chips in there. And that's true for other customers, other suppliers also. Then you got into what's called package on package, POP. That's the example I showed you with the Snapdragon, where, not exactly the same picture, but here's the logic chip. Flip chip means it's face down. And there's pads on this board that the memory can be attached on top. I think the example I showed you where this was all a molded compound, but similar, okay? It's a POP device. And then in the future, what he was talking about is through silicon vias, and I'll show you more examples of this. So this is where you might have, in this example, two processor chips. You actually drill holes through the silicon and have copper connections or some kind of high conductance connection going straight down, and then the same thing for the memory. So ideally, you could have 5 chips and the connections go straight down. Really efficient as far as performance is concerned. This has really not become production yet, right? And I'll show you some examples of where things are. So here's an example from Xilinx, I believe, right? Oh no, IMEC. So this is an example of what's called a interposer device. So you might have a stack of memory and a stack of logic. Now you connect them through a what's called an interposer that can have tighter lines and spaces and therefore better performance characteristics than a printed circuit board. See, a printed circuit board, the green stuff, the lines and spaces are very wide. They're on the order of mils, right? They might be 100 micron line and 100 micron space, for instance. And the silicon is probably a couple microns. So much better, shorter distances and better performance. So this is an example of what might be a 2.5D. Other thing that people are trying to do is this company Invensys is taking this kind of a DIMM memory and putting that into a single, it looks like a single package, and that helps product. So Invensys is probably a startup company and that took on this as a product. There was a need to reduce the form factor. They had a technology to build this, and I don't know what the performance is as far as business, but that's the way you take an idea and create a new solution. Who decides that is the customer, right? Whether the customer really is going to pay for that or not, and who the competition is going to be. Okay, Micron created what's called a hyper memory cube. Here's an example where you might have a stack of memories with vias going all the way up and down, making that connection, and that's pretty impressive. So I think that's in production. They worked with Intel, I believe, on that. Here's some examples of stack chips. So this is the 3-chip stack. Wire bond connections, all molded together. So from the outside, it looks like a single chip, but it's really got 3 in there. Here's package on package stacking. We showed you that. Within this one, there might have been an analog chip and a digital chip, for instance. And this one might have been a 2-chip memory stack. This one is where it's a side-by-side. And all of these are real in production type of situation. This one here is the through silicon vias, and it's from IMEC. So what you do here is that you've got, you got to follow me close here. So this is one chip, thick silicon, the interconnect layers where you have the connections and the vias. Then what you do is the second chip, you drill a hole, you thin the silicon, and you drill a hole and backfill that with copper, let's say. And so the top part of the interconnect layer is the same, and then a second chip, again with the through silicon via. You got to create a bond so that the top chip can come and sit and get attached. So this would be a stack of 3 different chips, one on top of the other. So conceptually it's good, and I think it's been demonstrated in the laboratory. I don't believe it's in production yet, because it's a pretty complicated technology and a lot of complicated business issues. Because let's say you're trying to, you build a logic chip and now you're trying to stack memory chips. Well, you got to have a memory chip that you can thin down and drill the holes in it. If you're buying the memory from Samsung, are they going to sell you the chip? I'm not really sure. How are you going to decide whether it's a good chip? And if once you stack it and it doesn't work, whose responsibility is it? So all kinds of business issues that need to get resolved, and in addition to technological issues. But those are still opportunities. I think they're... So I think this is sort of what I showed you before, is an HTC with a Qualcomm device that, in this case, you had a memory chip that got attached right on top of the logic chip, right? Now, there's a term that people are talking about called heterogeneous integration. So a lot of this other stuff was homogeneous, where you have same kinds of chips that are put together and the same package, so multi-chip packaging. Heterogeneous is where you might have a logic chip, but now you can have a whole bunch of other possible chips that you integrate either on a single module, a multi-chip solution, or a single substrate, right? So here's some examples from Taiwan Semiconductor Association, but I mean, it could be any combination of things. I'm just showing it visually. Intel came up with a similar solution where what they're doing is they got a package substrate and they create kind of like the interposer, but they bury the interposer within the printed circuit board. And what they're doing is you can mix and match your die. So you can have a logic chip here, you could have an analog chip, and you can connect them through a much tighter pitch solution with much higher, much more efficient interconnect. So this was just published very recently. I just read that a little while ago. And so that, again, they call it EMIB, is embedded multi-die interconnect bridge, right? So that's what that is. A lot of innovation in this packaging space, by the way. TSMC has got a 3D, what they call INFO, is integrated fan-out packaging technology. So here you got the base, the green substrate, a logic chip, this flip chip, and this is built using what's called copper pillars. Here's a more dramatic example of that. So in this particular case, you have the substrate, you build what's called little pillars that are sticking up from the board. You put your logic chip, and then you mold the whole thing. And then that goes to the phone manufacturer that can put the dynamic memory right on top of it. Here's where the multi-chip module could be memory and a logic side by side. So again, a lot of innovation. What it's going to lead to, is I'm going to give you a preview here, is that it's going to extend the life of Moore's Law in a sense. It's not Moore's Law in a silicon, but it's kind of a virtual Moore's Law that's happening. So here's an overall summary there of you got multi-chips on a printed circuit board, you got SOCs, and you can put them all together. You got 3D, that's 3D transistors. Oh, 3D can be two different things, right? 3D could be FinFETs on the silicon, and it could be 3D packaging, like I showed you with the through silicon vias, or wafer level packaging, or wafer on wafer. So these are all possibilities. And then there's system integration, where you might have a platform solution for mobile. Might be a logic chip, a memory chip, a modem, a transceiver, all a number of things put together. And that's where a lot of this system level co-design, right? STCO that we were talking about from IMEC. One way to try to integrate all of this, right? So we talked about the Moore's Law, the number of transistors going up and the nodes going down. In the old days, it used to be linear scaling for the Dennard theory. IMEC calls it happy scaling. Every 2 years, you would have a new generation of technology. Nicky Liu, who's chairman of Heatron and also the Taiwan Semiconductor president. He termed this thing, he presented this last year at ASSCC keynote speech. So I picked this from him, is that, so that was Silicon 1.0, right? That's what everybody talks about. Then around the 28 nanometer node, you started to do area scaling, where instead of just looking at the minimum feature size, you now talk about the gate pitch and metal pitch product of that. And that became good till about the 14 nanometer. Then you're talking about the volumetric scaling, where now you got 3D transistors and maybe 3D stacking in the package. What he's predicting is coming down is what he calls as a functional value creation scaling, where you might have heterogeneous integration in combination with design and architecture to create a system. And his contention is that as you do this, your overall virtual Moore's law could extend for another 30 years. That's Nikki's term. Whether they'll be there or not, I don't think I'll be around to see that, and you folks can probably see that, right? But his kind of the layout of what, you know, all the things about Moore's law, I think is a nice way to recap the whole thing. In terms of industry directions, according to Dr. Bahai, you know, in the past 20 years, you're doing a lot of commodity CMOS, it's dominant technology, it's here to stay. Markets are dominated by the next best thing, you know, next product. It's got to make business sense, very important. And the industry is characterized by huge volumes, a small number of products, right?